Welcome back, everybody. In this lesson, we're going to be talking about how to solve simultaneous equations using matrices, and in particular, how to use the inverse matrix to solve simultaneous equations. We're also going to learn to write a pair of simultaneous equations in matrix form, Ax equal b, where A, X, and B are all matrices. Now, let's talk about the why and how it works. So, how does it work? If we're solving a regular pair of equations, let's say, for example, we have 2x equal 10, and we want to solve this equation. Well, one thing we can do is to divide both sides by 2. Since the equation says 2x is 10, we can divide, and by dividing that, we can get that x is equal to 10 divided by 2, which is 5. This is okay for regular equations. We can do that. So ax is equal to b. We can simply divide both sides by a, and we get x is equal to b over a. The trouble is, for matrices, we cannot divide the matrices. So to get around this, we have to take an alternate route in terms of multiplying by the inverse of the matrix, or so to speak, we could multiply by the reciprocal, if you want to call it that. So here, for example, if we have our 2x is equal to 10, we could say then multiply both sides of this equation by the reciprocal of 2. So the reciprocal of 2 can be written as 2 to the minus 1 times 2 x would be equal to 2 to the minus 1 times 10. It's an odd way to write it. Normal people wouldn't do this. But 2 to the minus 1 times 2 is actually equal to 2 times 1 over 2. And that would actually give us the same result as x is equal to 5. So we take an approach like this in this situation, because we cannot divide the matrices. So here, ax is equal to b, where ax and b are matrices. We want to find what x is. So what we do is that we multiply by the inverse of the matrix. And once we multiply by the inverse of the matrix on this side, we get x. And then to get our answers, we multiply the b by that inverse. And this is called a pre-multiply, where we put the inverse in front of the other matrix. Post-multiply suggests that we put the inverse after it. So let's talk about pre and post. Pre-multiply, we put the inverse in front. So what are we saying then? We have a matrix equation. We can find our answer by multiplying by the inverse of the matrix. So we have 1 over a times a. That would cancel out and leaves you with 1 over a times b, which is the same thing as saying a inverse times b. Now, this is a lot of theory stuff, so let's jump into it and see what an actual practical example looks like without all this theory. But this is how it actually works. So let's say we have a matrix, a simultaneous system here. X minus y equal negative 5, and 3x plus 2y equal to negative 5. And we're supposed to write the equations in matrix form. The matrix form is ax equal b. So let's write that down. Part 1. So to write it down, what we do is that we look at the coefficients of the letters. The coefficient here is 1. The coefficient here is minus 1. So what we're going to do is this. To get our matrix form ax equal b, we put the coefficients in one matrix. So that's 1, negative 1, 3, 2. That's our A. Now for our x, this matrix is going to contain the letters that are in the equation, x and y, in that order. And the B matrix is going to contain what they are equal to. In both cases, it's the same number here. And so once we do this, we get the AX equal B. This is it. We have written them in the form AX equal B. Written the equations in the form ax equal b. The second part is to determine the inverse of the coefficient matrix. So this is the coefficient matrix. These are the coefficients for the numbers. So we can find the inverse of this matrix, of this A, And to find that inverse, remember what we need to do first is to find the determinant. So we can say 2 times 1. So let's call it the determinant of A, which gives 2 times 1, which is 2, minus 3 times negative 1 is negative 3. So we end up with here 2 times 1, 2, minus 3 times negative 1. That gives us 2 plus 3. And so our answer here is 5. So our inverse is going to be 1 over 5 multiplied by the rearranged adjoint matrix. So it's take this matrix and turn it into the adjoint by switching these two. So 2 goes here. This is negative, it becomes positive. This is positive, it becomes negative. And the 1 goes down to the other side. So we switch these two. Here they are switched, and we change the sign of these two. And so this is our inverse matrix. We can put that number inside it to make it a bit easier to work with, since we will have to work with it. So it becomes 2 over 5, 1 over 5, negative 3 over 5, and 1 over 5 again. So this is our inverse. Once we have our inverse, the question says hence. Hence solve for x and y. From our previous discussion here, we realize that if ax equal b is the matrix equation and we multiply both sides by the inverse, then what's going to happen is that we're going to get x on this side and a inverse times b on the other side. So let's see how it works out here. So to solve it, we're going to multiply the inverse times this. So we're going to have 2 over 5 rather, 2 over 5, 1 over 5. Let's write this a bit better and be a bit more consistent in how we write it. All right, 2 over 5, 1 over 5, negative 3 over 5, and 1 over 5. This is our inverse. And so the inverse multiplied by the coefficient matrix 1, negative 1, 3, 2, multiplied by xy. I'm not taking any shortcuts in this one. I want to show you the full process, and then after that I take some shortcuts. So again, the inverse times this, so you multiply both sides by the inverse. So it's 2 over 5, 1 over 5, negative 3 over 5, and 1 over 5. And that again is multiplied by this matrix, negative 5, negative 5. So when we do this, what happens? Recall from our previous discussions that if you multiply a matrix by its inverse, what you're going to get is the identity matrix, which is 1, 0, 0, 1. And that times xy would give us this over here. So let's take another step. 2 over 5, 1 over 5, negative 3 over 5, and 1 over 5. Multiplied by negative 5, negative 5. Also, remember that this matrix, the identity matrix, is the identity element under multiplication. So when we multiply this matrix times xy, we are simply going to get back xy. 1 times x plus 0 times y gives us x. 0 times x plus 1 times y gives us y. So this simply gives us xy. And it's telling us that xy is equal to the product of these two matrices. So what we need to do then is just to multiply these two matrices to find our answer. This is a 2 by 2, this is a 2 by 1, so we can multiply 2 times negative 5 here. 2 5s gives us negative 10, plus, that's 2 times negative 5, plus 1 times negative 5 gives us another negative 5. All of that divided by 5. And Here, negative 3 times negative 5 gives us a 15 plus 1 times negative 5 is negative 5 all over 5. And let's tidy this up. Here we see that x is equal to negative 10 minus 5. That gives us negative 15. And negative 15 over 5 gives us a negative 3. And here we have positive 15 minus 5. That's 10. And 10 over 5 is 2. So we end up that y is 2. And so this is how we use the inverse matrix to solve a pair of simultaneous equations. I went through all the steps in this example to show you how it's done by not taking any shortcuts at all. So what we do is that we wrote this simultaneous equation in matrix form. Here it is, ax. This is the A matrix. This is the X matrix. This is the B matrix. Ax equal B. Find the inverse of that A matrix, which is also called the coefficient matrix. And once you find that inverse, we do a pre-multiply. That is, we multiply right across. We multiply both sides. Notice that I said pre-multiply, meaning that the inverse matrix comes first. So the inverse matrix multiplied by this, and it's also in the same position here. That's also important when you're doing multiplication. You do not want to start with the inverse matrix on this side, but on that side of the equation, you put it on the other side. Remember that when you change the order for matrix multiplication, the result is not always the same, so you have to be wary of that. So if you're going to pre-multiply, go ahead and pre-multiply. In this case, we can only pre-multiply anyway, and keep it consistent. So once you do that, matrix multiplied by its inverse give you identity. Identity times xy simply gives you xy. So all of this comes down to just that. In previous questions, I will not be going through this. I'll just go straight here. And what you do to get your answers now is just to multiply your inverse multiplied by the B matrix here. And that gives us our answers, x equals negative 3 and y equal 2. Let's try it again with a different question, of course. So if we have a equal 3, 2 to negative 3, this is how CXC writes some of those questions, then we can first evaluate the determinant of a. So let's find the determinant of a. So part A of the question says determinant of a is going to be equal to negative 3 times 3 minus 2 times 2. That gives us negative 9 minus 4. And that gives us negative 13. That's our determinant. After that, now we are told to evaluate, it is to determine rather, A inverse. And to get A inverse, part B, we simply need to say 1 over determinant multiplied by the adjoint matrix. So we switch these two. So negative 3 goes there. Positive 3 goes here, and we change the signs of these two. So this becomes negative 2, this becomes negative 2. They were both positive, so we change their signs. And now we can write down our inverse, nice and tidy. Negative over negative here gives us a positive, so that's 3 over 13. That's 2 over 13 by the same argument. Negative divided by negative, same here, 2 over 13. And the last part, and negative 3, this is positive, that's negative, so negative 3 over 13, this is our inverse. This is A inverse. Once we know A inverse, that's part B. Part C says, using the inverse, using A inverse, solve this system. Notice from the question that this matrix is the coefficient of matrices for this. So 3, 2, notice it, 3, 2, 2, negative 3 is the same, and 1, 5 is the answer matrix. So to solve this system, we are simply going to say, therefore, xy is equal to this inverse matrix, 3 over 13, 2 over 13, 2 over 13, and negative 3 over 13. Let's pull this down a little bit more. And we're going to multiply that by the b, which is 1, 5. That's all we need to do. We do not need to go through the long steps that we took earlier. in this question where we discussed the entire thing. So we found the inverse to multiply it by that side and that side, 1001, only to get xy equal. So we can avoid all of that now that we know. So we can just say xy is equal to the inverse times the b. Now, let's multiply this. So 3 times 1 gives us 3 plus 2 times 10. 1 times 3 is 3. 2 times 5 is 10. All of that over 13. And 2, this row times that. 2 times 1 is 2. Plus 3 times 5, that's negative 3 times 5 rather, is negative 15. All of that over 13. And so from this we see that 10 plus 3 is 13 over 13. And that gives us 1. And 2 plus negative 15 is negative 13 over 13, which gives us negative 1. So we can see then that our answers are x is equal to positive 1 and y is equal to negative 1. And those are our solutions from using the inverse matrix to solve this particular system. We have one more question. This question has 4 unknowns. 4 unknowns. And A, B, C, D, it has a coefficient matrix 1, 4, 2, 1. So we're to write down the inverse of matrix V. Remember, to find the inverse of matrix V, we first need to find the determinant. So the determinant of V is equal to, what is it equal to? 1 times 1 minus 2 times 4, which gives us 1 take away 8. And so our determinant is negative 7. Because our determinant is negative 7, our inverse is going to be 1 over determinant multiplied by, switch these two, which doesn't matter right now because they're the same number. And these two change sign, so it's negative 4, negative 2, and 1. And this gives us, when we put that fraction inside the matrix, negative 1 over 7, positive 4 over 7, negative and negative. Here, positive 2 over 7, and negative 1 over 7. So this is our inverse. Once we find our inverse, we can now use it to solve this system of equations and get our answers for A, B, C, and D. And what we're going to do now, since our coefficient is on this side, we definitely need to pre-multiply. So we're going to write down our inverse, which is negative 1 over 7, 2 over 7, 4 over 7, and negative 1 over 7. And that let's tidy this up a little bit. Let's write it a little better. All right, there we go. Negative 1 over 7, 2 over 7, yes. 4 over 7, better, and negative 1 over 7, okay. And we're going to multiply that by 1, 4, 2, 1. A, B, C, D. Just taking the long road here a little bit. And that is going to be equal to this inverse, negative 1 over 7, 4 over 7, 2 over 7, negative 1 over 7, multiplied by, just writing out the whole thing so you can see it, 4, 13, 8, 5. And so what happens is, all of this will turn out to be just A, B, C, D equal to this product when we multiply it. So let's multiply these two matrices here. Now, 1, we're going to multiply row by column. So 1 times 4 is negative 1 times 4 is negative 4 here. And 4 times 8 is 32. All of that over 7, row by column. Also, row by column here, negative 1 times 13 is negative 13, plus row by column, 4 times 5 is 20, over 7. So row by column, row by column. Next, we have this row multiplied by this column. So 2 times 4, that gives us 8. And 1 times negative 8 gives us negative 8. All of that over 7. And 2 times 13 gives us 26. And 1 times negative 5 gives us negative 5, all over 7. So what do we get then? When we compare all of this, let's look at what it says. Negative 4 plus 32 gives us 28. 20 here minus 13 gives us 7. 8 take away 8 gives us 0. And 26 take away 5 gives us 21. And when we simplify all of that, what we get is 28 divided by 7 is 4. 7 over 7 is 1, 0, and 3. And so we know what our values are. A equal to 4. B is equal to 1. C is equal to 0. And D is equal to 3. And so we can use inverse matrices very effectively to solve systems of linear equations, whether they systems of simultaneous equations or simultaneous linear, whether they have two variables as in x or y there, or whether they have four variables a, b, c, d. Using the inverse matrix is a very useful tool, very indispensable tool actually, in solving this kind of equation. So we can use them. Once we know how to use it, multiply that inverse matrix by the B matrix, and you get your result. This is how we use the inverse matrix to solve systems of linear equations. Remember to subscribe, hit the notification bell so that as soon as these videos come out, you will be notified. Continue working hard as you prepare for your CSEC exam, and best wishes. Thanks for watching.